Good morning and welcome to the webinar, everyone. This is the fourth in the four-part series. It's been a real wonderful learning experience for all of us. Just a reminder, if you have questions during the webinar, you can go to the bar where it says questions, put your questions in as you think about them, and we'll get to them at some point during the webinar. And so I'm very happy to introduce our esteemed speakers, Jose Ramirez and Feng Chen. So let me turn it over to them and we'll begin now.
Yeah, we're going to turn our video off to maximize the bandwidth.
Yep, me too.
Hopefully you can see the screen. Good morning, good afternoon, and good evening. And as we joked last week, if you are watching this webinar on a Friday night, hats off to you and our deep respect for you. So we're at the end.
You put us over the Olympic Games, so during this time.
Yes, so we are at the end of our tour, and so thankful to all of you and for the feedback that we have received. We're so glad that this has been helpful and you find some value on this. But this is kind of like the moment we've been waiting for. Today, we're gonna really get into using prior knowledge, all this historical information that we have, especially in CMC, to take full advantage of the Bayesian techniques. So these, we have shown you this a few times before. This has to do with non-informative priors. This is the non-committal type thing. People, Fang always cringes when we show this because, this defeats the purpose of Bayesian statistics. I mean, the whole point of Bayesian statistics, as you've seen, is to be able to use this prior information to inform and improve, our decisions.
But I think on the same note, from a practical perspective, there is a utility of using consent, everyone agreed upon non-informative prior, in the sense of people feel that it's a battle when it doesn't need to fight, and then it also have to speak for themselves. So there certainly is a utilitarian usage of non-informative prior, or to do so. Yeah.
So let's talk about informative priors. I'll let you look at that cartoon, maybe a little small. And they're trying to decide if the sun has gone nova. And our money here is too with the Bayesian because we do have prior knowledge. We have thousands and thousands and thousands of sunrises in history. So
billions, maybe billions of sunrises.
Billions of sunrises. So that's a pretty strong, a truly informative prior, and that's what the Bayesian is betting $50 on that. So we may not have billions of data points for that, but in CMC, we do have a lot of historical data that can be used to generate good, quote unquote, informative priors. So talking about informative priors, so we need to summarize that information. It's a subjective information of an unknown, and this unknown is the quantity of interest. We show you the frequentist and Bayesian diagrams before, so we have something. It may be we want to predict expiry at a certain time point, 36 months, 48 months. We may be looking at the difference in means like we did last week for biosimilars, or a variance ratio. So that's the unknown. So we need some information, and we should elicit that information. And we'll talk a little bit about that. But the key here is how we can connect that information that in CMC, as I mentioned, is based on data. How do we connect that data to parameters?
Right, because in most cases, a practitioner knows what the data look like. they don't know as what the parameter distributions is like. So it's of essential importance to be able to, if you ask a practitioner what's the beta regression in this nonlinear model with negative binomial likelihood, they don't know. They have no idea. They won't know any better than we do. But then they have a sense of the data. So it's the connecting between the information that's contained in the data and how to translate that into on distribution form is what's of the essential interest.
And we're going to show you some of that translation
Right.
in a couple of examples today. So things that to think about, I mean, sometimes I think of these as useful priors. I just think about a posterior distribution is just a weighted likelihood. Remember, but we mentioned that even though we may argue in methodologies and philosophy and interpretation, at the core of both the frequentist and Bayesian approaches, we still have the likelihood. So, and the posterior is just a weighted likelihood weighted by the prior distribution. Gelman, back not long ago in 2017, they put a paper out, and they're talking about the practical utility of a prior. And this is not that different from what Professor Box and Professor Chow were talking about in 1962. That says, we sometimes ignore what the sample has to tell us about the matter in question. And that happens to a lot of us, and especially sometimes the people we work with, scientists and engineers, we just eager to apply a technique and we just run it, especially these days that it's easy just to add the data to software and get an answer. And sometimes we forget about the data itself. But here the point is that, we have to look at that connection between the likelihood and the prior and also the posterior. And so.
Yeah, and the keyword, another way to look at the same thing is that the idea of objectivity. When people talk about objectivity, they really are trying to say they pretend they don't have a personal opinions to the matter, as if that was the true ways of doing things. But the objectivity is at the same time as the disregard of prior knowledge, which by itself is also could be problematic.
Yeah. And another key thing, and we have mentioned this several times, parametrization is important, and we'll show you a few of those things. One of them is looking at the negative binomial as a gamma Poisson, and this helps with the structure of the problem, that translation between the data and the distributions and the parameters, and also setting up priors and all that. So something to remember, the parametrization is important. So we're going to look at 3 ways of using prior knowledge. One way is empirical based. Some of you may be familiar with that. And the idea there is we're going to use the data, the historical data, to estimate the prior information. Another idea that is very popular in the Bayesian approach is the hierarchical models. And the way I think about this is like a random coefficients model. And we'll spend some time explaining what a hierarchical model is. And the final one is the power prior. For me, it's a great way of combining information coming from different sources, and it allows you to weigh that historical information relative to the likelihood. So it's a nice way of combining the prior information with the likelihood. So remember this data set with 4 observations. So we're going to start there. Last time we looked at this data set, we did the frequentist approach for this. We wanted to get an upper bound. These are 10 microns subvisible particles, and whenever you have subvisible particles, you want to get an upper bound for that because you don't want to exceed that. So here we had a situation where we have a very small data set, only 4 observations. That stretches the limits of the frequentist approach. So we did that, we got a limit, and we also did the Bayesian approach with a non-informative prior. So what we're going to do today is we're going to show you how we can incorporate additional information, historical information, to see what happens to those estimates. Again, the parametrization is important. This is just to refresh our memory. We're using the gamma Poisson mixture parametrization that is right here. And we have the parameters phi and p, where p is the probability. Yeah. So we have this data. Remember that we use diffuse priors on phi and p. We did that, and we got upper bound of about 3,900. If you do the frequentist approach with the negative binomial, you get about 4,500. So we say improvement in the upper bound because it got smaller. Sometimes too wide of a limit can be an issue. Yeah. But that's not a surprise because, as you know, statistical intervals should reflect the uncertainty in your data. So as the sample sizes decreases, then there is more uncertainty and the intervals tend to be wide. So, and that's what you saw with the frequentist approach. 4 data points, you get a limit, an upper bound of 4,500. And the Bayesian approach with the diffuse priors, again, we put improve in quotes, just to reflect that, gives you a smaller interval. But can we use historical data? If we have historical data, and as we have said this many times in CMC, we do have this historical data because we have molecules, different molecules that are related somehow. And for processes like this, which is the subvisible particles, is common to a lot of the molecules. It's not, as far as I know, molecule specific, or maybe a family of molecules specific, but not just to a single one. So we're going to show you how to do this using empirical Bayes, and we put it in quotes because this is a variant. For those of you who are familiar with empirical Bayes, this is slightly different, but in the same spirit. And then we're going to show you how to use a hierarchical model. So this is our data, only 4 samples. And it's over dispersed count data, which means the Poisson distribution is not a good approximation. Can we use data from similar products? And you have a data set right next to it. And that data set has a lot of points, okay? So we're gonna start by combining the data set with 4 observations with this other data set. Okay? So we're gonna start with empirical Bayes. And the empirical Bayes goes back to this paper by Robbins in 1956. And the question that he was asking is, well, if I'm trying to do this patient, but I have previous samples, x1 through xn minus 1, and a quantity of interest can be the lambda of a Poisson distribution that you want to estimate. And G lambda is a prior on that lambda parameter. Can we use that information to get some prior? And what he did, and it's a very nice, for those of you who are into this, I recommend you look at the paper because it's a very nice way of using that information to derive that empirical distribution of the random variable. And that's why this is called empirical Bayes. Yeah.
One of the frustrating thing in Bayesian computation is that you have to specify your prior, which also means you have to specify your uncertainty. And in the context of random effects models, you still have to say how the random effects, for example, are shrinking towards each other, and that it turned out to be a pretty tricky thing to do. So the idea of empirical Bayes estimate, which is to say that since we have data that we know that they are shrinking towards each other in terms of cluster effects, then why don't we just using the data to inform how much the amount of shrinkage that need to be? And that's the idea of using empirical distribution function to figure out what the prior distribution should be. Has its problem, but it's a practical way of doing it. Yeah.
Exactly. It's a very practical way of doing this, and again, the key word here is inform. So this is the main idea. We're not gonna do more details. The paper, the reference for the paper is in the back. That is a non-parametric way of doing it. There's a parametric way of doing the empirical Bayes. You're getting the prior and the estimates from the data, usually using maximum likelihood. We show you that. So for the subvisible particles, SBVP stands for that, subvisible particles. With 4 data points, we use the gamma Poisson, the negative binomial with the parameters 5 and P, and then for the 5, we use a gamma with parameter shape and inverse scale, and for the P, because it's probability between 0 and 1, we use the beta distribution. Now, the parameters of the negative binomial distribution are going to be estimated via maximum likelihood. And that's going to give us a parametrically estimated, so to speak, marginal density. And then once we have those parameters, we're going to use the phi hat and p hat, the maximum likelihood estimate of those 2 parameters, to derive the shape I scale alpha and beta. And you may be thinking, how are we going to do that? You may be thinking that we're going to get into a mathematical exercise with a lot of equations and try to figure out how to go from the phi hat and p hat to the 4 hyperparameters. But actually is a little easier than that. So here you can see a view of the data with 4 observations, and this is a data set with 199. So you can see just visually that, you can think of that, yeah, they probably belong to the same family of distribution. So we have a large data set, and we make this joke before that, big data and all that. I mean, for us, a data set with 199 observations, that's as big as it can get, when you're in the CMC environment. So we do have a pretty large data set, 199 observations, that we're going to use to estimate the parameters phi and p. So we use our maximum likelihood estimation. This was done with PROC NL-mix because we just write out the likelihood, and NL-mix is pretty good at fitting nonlinear mixed models. We put in here that 199 is good in the sense that it's going to have pretty good asymptotic properties. Again, 199 is a very large number. So the phi estimate is 25420, and the probability is a small 0.03289. So now we have these two parameters. Okay, we have estimated these two parameters from this distribution here. We grab this distribution, we put the data through PROC NL-mix, and we got this. Now, how are we going to use that to derive the parameters of the gamma distribution and the beta distribution? Remember, those are the ones we need for the prior. Okay? So the trick here is that we are going to center these distributions around the LMEs. I want this distribution for phi, the gamma, to be centered around the 254 with this standard deviation. And for the beta distribution, I want it to be centered around this value, okay, with that standard deviation. And
Yeah.
thank you. Yes.
Yeah, in other words, what we want to do is we want to find a good gamma distribution approximation to what the MLE estimates and standard error, and the beta to the same thing. So that's the idea of
Exactly.
capturing the essence, parametrically capturing the essence of those prior distributions.
Yes. And how do we capture the essence? I already mentioned that it's not a mathematical exercise. Thank you to Fan and his team at SAS. They have this macro called distinfo, D-I-S-T-I-N-F-O. And essentially, if you notice what we're doing here, we're telling this macro, I want this distribution gamma. I want to know the parameters of the gamma that are going to give me a mean of 255.04, which is this estimate, with a variance which is this square. It's that simple. And for the P, I want to find the beta distribution. I want to find the parameters of the beta distribution that are going to have a mean of 0.00239, which is this MLE here, and with this variance, which is this standard deviation square. And the macro actually comes back and tells you what the shape and I scale are for the gamma and what the alpha and beta are for the beta distribution. That's simple. So the macro told us that the gamma parameters are 111 and 44. A gamma with those parameters has a mean of 2.52273. And notice this is close to the 0.54204. The variance, if you take the square root of that, you get close to that. And for the P, the beta distribution with alpha 91 and beta 27,000 and 610 has a mean of 0.0329. 0.0329, and those are the way those prior distributions. So again, what we did was the following: we have an additional data set with 199 observations. We assume that it's also going to follow the negative binomial. There's a good approximation for that. We use maximum likelihood to estimate the phi and p from that distribution, and then we come into this macro and we want to find the parameters of the gamma that is going to be centered around the maximum likelihood estimate, and it's going to have that spread. It's not just centering, but centering and spread. And we do that for the distributions. And it's my understanding that the distinfo macro supports all of the distributions that you can use as priors within PROC MCMC. So in essence, they have made our life easier. Now that you know what to do, then those macros are very helpful. So now, what we're doing is we're going to take those priors with those parameters and we're going to fit that. Now, we're putting this in quote because this is a little bit different from the traditional empirical base that you're used to. In the traditional base, you use the same data set to generate those estimates and the priors. Here, we are using an external data set for that. And why we use a separate data set? Well, we have prior knowledge. That's, again, in CMC, we have knowledge about subvisible particles for a whole bunch of molecules for a whole history of that.
And it is also translating the information that's contained in the data to the parameter space. So that's just to show you one way of doing so is that with it.
Exactly. And thank you for bringing that up. Remember, this is one of those key things that we have to connect the data to probability distributions and parameters, and we just show you how to do that. Another way is this data set, one of the assumptions that can be approximated by the same likelihood, in this case, the negative binomial. And again, we have history on that, and it's very reasonable to do that because we have used that negative binomial with other subvisible particle data set. At least I have in the 10 years I've been at Amgen. Now, again, a sample size with 4 observations is very small, so you saw the intervals are very wide. And if we try to use that to get estimate for phi and p, those estimates are very soft because the asymptotics don't help there. But the prior knowledge data set has 199. And this is, for me, I mean, some of the purists may not agree with me, but this issue of the empirical base using the same data set for me is double dipping because you're using the data set to generate the parameters on the priors, and then you're using the same data set for the Bayesian analysis. So the prior and the data set are connected. And there may be advantages to that. But for me, it's like double dipping in quotes. So that's why we put this empirical base in quotes. But now let's look at the code. Now that we have the priors, we know what the priors are.
Yeah, so the prior, if we know what the approximating prior need to be, we know what the parameters that need to, and they essentially capture data information from the 199 observation data sets, and there are the gamma with the shape and in scale parameter, I scale parameter, and the beta with 91 to 127,000 beta parameter.
What and by the way, yeah, this is a typo. This should be 44.
44. Yeah. So one thing that you probably do, and probably is coming across your mind, is that we have a data set that has only 4 observations, and we are using a data set that has 199 observations, and using that information to construct a prior in the analysis of the 4 observations. And you might think that the prior information is going to overwhelm information that's contained in the current data set. So there are 2 ways of looking at it. One is that if the expert, which in this case, a subject matter expert, have seen lots and lots of data, they probably do have a pretty good idea of what the data should look like, and the alarm would go off if things gets too large or things gets too small. This is just a formal way of statistical representing it. But on the other hand, if we didn't do it here, but if you were to think that this is too informative in the sense of it contains too much of the information from the prior, you can always choose to use a diffused prior in the sense of you can mixture a gamma prior with a uniform prior that give you a greater range of the phi, the distribution on phi, or a beta prior with a spiky beta prior on the small probability values with a uniform prior on between 0 and 1. And that's always, that's just, we are in the realm of using some information, informed information, but also protect yourself against having too much information.
Yeah, and I think that's one of the nice things about the Bayesian approach that allows you to do that.
Yeah, and we just didn't do it here because we don't want to make things too complicated, and we just want to illustrate the points of constructing prior.
Yeah, exactly. And so this code is the same as we used before. The only difference is that before we used these priors with very small numbers here, and in the 1, 1 to be a uniform between 0 and 1, we made them diffuse. Here, we are specifying the parameters. That's why these are informative priors. And again, once we use these numbers, then they're going to be centered at the MLEs for the 199 observations data set. And as we showed you before, you have the quantile function, and that's how we're going to get the upper bound. Just put the negative binomial there, the coverage that we want, which is 99%, and then the probabilities on the phi. And again, this is the beauty of this, that once we have the posterior distribution for the probability of the parameter P and the posterior distribution for phi, then we can just pass that in there and we get a posterior for the quantiles. So we just want to show you what the informative prior does. On the left, you have the joint distribution of phi and the probability, parameter P, using a diffuse prior. And you can see, that's why it's called diffuse, because your knowledge is, you know, all over the place.
Because there's only 4 data points that we do expect a much wider range of both phi and the P in this sense.
Now, when we go to the informative prior, what it does is concentrate that information. Now, because remember, the probability P that we estimated via MLE was 2.52 something, or 2.54. So this is centered around 2.5, and the probability was 0.003 something. So this is centered around there. So that's why the mass is there. So you can see that. And then just the one-dimensional way again on the left, the diffuse priors, on the right, the informative priors, and then the concentrating that. Again, this is a parameter phi, which is 2.5, and this is the probability, which is 0.003. And then these are the parameter estimates from the two runs with the diffuse and the informative priors. But one thing that we want to bring to your attention is the standard deviations. Notice how they decrease when you use informative prior. So that's the, you know, Fang used the word, we're informing this data set, these 4 observations with the information in 199, and that helps to improve the precision of the estimates. And that in turn is going to help with the upper bound, because the upper bound is a function of the variation in those parameters. So if you look at the upper bound that we get with the empirical base, it's about 2,700. Yeah, and we'll talk a little more about this when we compare it with the hierarchical model.
Right, and if you think that the range of Bayesian diffuse prior is 3,800, and then using 199 observation on top of the 4 observations, that you get a range much smaller of 26,700, then you know that by borrowing partial of information, if you were to use a diffuse prior, for example, then you would get an estimate somewhere near that between the 2 range. And it's the effect of smoothing the information that you control on how much you want to use in the analysis for it.
So now we're going to go to another way of doing this. Again, that's empirical based, and the idea there is, if you want to be a traditionalist, you can use the same data set to inform the parameters and the priors that you're going to use. Or if you're like me in CMC that has a lot of prior knowledge information, you can use that prior knowledge to inform the parameters and the priors, like we just showed you. Now we're going to use the same example, but now we're going to use something that's called Bayesian hierarchical models. And in a hierarchical model, what that allows us to do is to use multiple data sets, okay? Before we use just one. Here we're going to use multiple data sets because, as we mentioned before, you had data for other products and molecules on visible particles. So why just use one? Can we use more than one? And this is where the hierarchical models come in. So we're going to have multiple levels or submodels. We're going to capture the dependence between the observations within a given data set. So that will be kind of like the within variation. And then we're going to capture the variation data set to data set. And that's, you know, it helps me think of these hierarchical models as random effect models, because that's what we're doing, we're capturing the variation. That's what we call the random effects. And you'll see that in the random effects statement. We showed you that last week. And the key word here is we're going to borrow information from all these different strata in the hierarchy. Okay?
Right, because the basic assumption on the random effects model is this is a way of you know you have different clusters of data, and they are not the same. They might be very similar to each other, but you are unwilling to make the assumption that they are the same. If they're the same, then you have a fixed effects model. You have a regression model, which you don't really want to do. And but the random effects from different clusters, the parameters themselves, they help each other to estimate. I'm using all information from other cluster to help me estimate my parameter, and I'm using my information to help everyone else to estimate their parameters. And that's what the borrowing information idea comes from. It's also the shrinkage estimate. So.
Yes, and for me, that also reminds me of this gamma Poisson model. If you think about that, sometimes when you're dealing with count data, you have a Poisson and you have a parameter lambda, but you may have different clusters and they have different parameter lambdas, and that lambda gets a gamma distribution, and that's the gamma Poisson mixture. In a spirit, it's kind of the same idea, but this is the power of this technique. You know, we're gonna be able to borrow information from other data sets. So again, here, yes, you want to say something? Fine.
Oh, I was just going to say that the purpose of just echoing on the idea of over dispersion, the purpose of random effects model in one sentence is the trade-off, a very bias and variance trade-off, because you do actually better than putting them all together, and better than if you treat them separately. So somewhat shrinkage estimates that's just basic statistics. Just want to say that. Yep.
Yeah. So here we have two additional data sets. This is the data of N4. This here is 199 that we just used for the empirical base.
Oh, we lost you. Hello?
We have two other.
Oh, sorry.
Hello?
Hello? I think I couldn't. I lost you for a second.
Hello?
Yeah. Yeah.
Oh, okay.
Yeah.
Okay.
Yeah,
What I'm saying here is that the bottom. Can you hear me? Yes. The bottom data set is the 4 observations that we have. This layer here is a data set with 199 observations, and we have 2 additional data sets. One with 63 observations, one with 28. So what we want to do is use those 3 data sets with the data set that we have, and use that data set to data set variation to borrow information from D1, D2, and D3. And as I just mentioned, we did the empirical base with D3, the data set with 199. Okay, so we're going to have to specify a likelihood. And again, in this case, based on the knowledge that we have, that we're dealing with over dispersed count data, we use the negative binomial, same parameterization, phi and p. Now we need to specify, now we're talking about hyper priors, you know, because you'll see a diagram with the different layers or levels of these. We need to specify priors for the phi, I, and pi, because are the random effects. In essence, each data set, again, is going to have the same likelihood. So each data set is going to have a negative binomial. So you're going to have a phi I and pi for D1, one for D2, one for D3, and one for D4. And those are the ones that are going to capture the data set to data set variation. And again, this is where you can, if you're familiar with mixed models, this is like the E-bloops for the random effects. You have one for each of the members of that class of variation. And then we're going to have to specify hyperparameters for the priors that we're going to use there. So for the negative binomial, we have these conditions. The parameter phi has to be positive, has to be greater than 0. And as you know now, the p is the probability that has to be between 0 and 1. Because this parameter has to be greater than 0, one thing we can use is a positive distribution. In this case, we're going to use a log normal with parameters log psi and variance psi. And then these go 1, 2, 3, 4. The 4 is the current data set. 1, 2, and 3 are the historical or the prior knowledge data set. That's why we have the 3 plus 1. And then here, the random effects 4, 5 are going to have some priors too. So the prior for log psi is a normal with a large variance, and the prior for the variance, as you have seen before, is an inverse gamma. Now,
right. I want to just add a quick comments on here. Typically, if you do have, say, you have 4 random effects and you specify a prior distribution on them, and you can just say that I think my random effects just log normal center at 0 with certain amount of variability as 2 sigma phi, and you can pick a value to say 20. This most people don't feel comfortable doing that because the specific value, the fixed value of the 0 and the 20 of the variance of the log prior controls the amount of similarity, information borrowing across different random effects. They are similar, but they are not the same. But how much they are similar is controlled by their prior. And so typically, we have another layer of the prior on top of these hyperparameters, the log phi and the sigma 2 phi, to have their distribution to express. We don't really know what values they should take, and the data would help us inform it. So that's why we have an extra layer of the prior on top of them.
Yeah, so here things are getting a little more, not complicated, but a little more elaborate. And this is the only thing for us here is to keep track of things. And I will show you a diagram. And this is what you need to keep track when you're going to write the PROC MCMC code. But if you have an idea of the structure of the hierarchy, then it's easier. And again, for P, which is a probability, we're going to use a beta distribution. And then the parameter theta is 1, 1, and the parameter K is gamma. Now you may be seeing that and don't recognize that, because normally when you see a beta distribution, it's alpha and beta. This is a slightly different parameterization, and we're going to talk a little bit about this. Again, this parameterization is important. So we're just sharing with you the tricks we have learned that are very helpful. So it is helpful to write a beta distribution like that. So we have that, and this is a diagram. So you have the data at the bottom. We have 4 data sets. The 3 historical ones are the prior knowledge, and the 4th data set is the 4 observations, pun intended there for that. And each of those data sets has a negative binomial with phi I and pi. Now we go to a level above, and the phi I are log normal, log psi, sigma squared psi. The probabilities are beta with theta and k, okay? And then for the log normal, the mean, the log psi is normal because the log of a log normal is normal. And then the variance is an inverse gamma. For these parameters, the beta, the theta is a location parameter and center on the mean. So we're going to use the beta 1, 1, which is the uniform in 0, 1. And this k acts as a dispersion parameter. So we're going to use a gamma distribution.
And in the middle layer is random effects, and on top is called hyperparameter. And the MCMC program essentially treating the middle as random, and on top is as hyperparameter. That's it.
So these are the random, and these are the hyperparameters.
Yep.
Just briefly, so this parameterization of the beta distribution. So remember, I said we're familiar with the alpha beta. In this case, alpha is theta, kappa minus 2 plus 1, and beta is this, is 1 minus that. So theta is a location parameter, and k is control that. You can see parameters that allow us to control that. So for increase k, the dispersion decreases. So you're more concentrated around that, and the location parameter just moves where you are. This is 2.5, this is 0.5, this is 0.75. So this, for us, is a nice way of controlling the beta distribution in terms of something that we as statisticians are very familiar with, which is location and dispersion. Okay? So just a little side there. So here's a code for that. So this is a little different because it has arrays.
Yeah, the code itself. So the arrays control the arrays of the parameters array of representing from the prior information of these parameters, and then oh, sorry, my can you hear me okay? My screen is freezing a bit. Maybe I have bad internet.
Yeah.
Okay.
Yeah, we can hear you. We can hear you.
Okay, so these are the parameters array of the phi, prob, and the lambda arrays for these things, and then each have the size 4 because they represent the 3 prior, 4 data sets. I mean, that's in essence what that those are. And then the hyperparameters are the log psi, S2 psi, and the theta and the kappa. So 2 of them is for random effects phi, and 2 of them is for random effects pi. And you can see that in the next four lines represents the prior distribution, the normal, the inverse gamma, and the beta, and beta for theta, and then the gamma for kappa prior. And then I think we used a lower bound on kappa to prevent it from getting to be too small, to be too for
That's
the
right.
analysis set.
Yeah, actually, that's something I forgot to mention in the previous slide. Kappa has to be greater than 0, otherwise things do not work. And that's why we have the lower there. And that's, again, one of those nice things that MCMC has for the distributions. You can specify a lower and an upper. But as we were saying before, if you have kind of that idea, that diagram, it's a little more elaborate, but if you keep track of things, then these matches these. So the hyper priors match the ones on the top, and these were the hyperparameters, as Frank mentioned. And then on this side, we have the random effects.
Right. The random effect, essentially, we use notation of rand phi to just remind ourselves it's random effect for the phi and random for the prop. And then they have their normal and the beta distribution. And notice that the beta prior has that dispersion parameterization, the theta and kappa as a function of the two. And then we also always have to follow the subject equal to indicate that the subject in data set. Data set is in the data set, it's just 1, 2, 3, 4. There's 4 different values, and then PROC MCMC knows internally to generate 4 sets of rand phi and the rand prop. And then the likelihood is the user-defined likelihood of the gamma Poisson likelihood with a transformed. It's not transformed. It's the same as just renamed phi of the random effects, and then this. So the next slide, this portion is to keeping track of the posterior means, and that's what we store them in the array. In the array of a phi of the, there's 4 of them, and then this D index is a data set index that goes from 1, 2, 3, 4. It depends on which cluster of the data that a particular observation belongs to. So when observation of dx is equal to 1, it computes the phi ran 1 for cluster 1. And
for
so
data set 1.
For data set 1. And
yep.
as it advanced to data set value 2, then computes for data set 2 and so on, because the input data set, the value of D index changes from 1, 2, 3, 4, then it knows which array is being computed on. And then the population parameter is the transformation, the phi population parameter, transformation of the hyperparameter, the log of phi psi, and the lambda is the corresponding transformation. That's it. And this is the caterpillar. Oh, okay, go ahead.
Yeah, no, this is a caterpillar plot. On this side, we have the phi, and this side we have the probability. 1, 2, 3, 4, the 4 data sets. So data set 4 is here. Those are the parameter estimates. And then this is another view, so you can match it to the data set. One thing that you can see here is that the phi parameter is similar for data sets 2, 3, and 4. It's all here. For data set 1, it's a little lower. And the probabilities for data sets 3 and 4, the probabilities are very similar. And for data sets 1 and 2, the probabilities are similar. And we're talking about similarity in terms of the mean. The dot represents the mean. The lines represents the HPD. Sorry, the credible interval. But it's just to give you a sense for what they represent with respect to the data.
To notice here is that when we start doing analysis, we don't really know how similar or dissimilar these 4 data sets are. And we do have experts who tell us that they are more or less belong to the same cluster. They are similar enough. And from the estimates point, you can see that the random effects is able to somehow decipher them into differences. Some have similar probability more close to each other than data sets 3 and 4, than 1 and 2, and some of the shape parameters is 2, 3, 4 is different from 1. And you can see from the estimates, there is not an overwhelming amount of borrowing. In other words, we are not treating the entire data set as a fixed effect. Not everyone is the same. They are slightly different, but they're decidedly similar. So that's the idea of random effects model.
And these are the results of all the things that we've done so far, so you can see what's going on. So if you look at the empirical base that we just did, that was 2,700. that tends, as Fan has mentioned, it shrinks the posterior towards the data. So the line at the bottom, the 2533, that is the upper bound. If you just grab the 199 observations and do a frequentist upper bound, you get 2533. So you can see that, in fact, yes, the empirical base that we did, which derived the priors and the parameters of the priors from the MLEs of the 199, it does goes there. Now, if you do the empirical base, you can see how the empirical base borrows information, as Fan just said, from the other data sets and improves the precision. Now we go from 4,500 to 3,500. So it's not as, as drastic as using the empirical base. It's somewhere in between, and Fan alluded to that before.
Right.
So again, these are the different ways of doing this. So we have shown you two ways of using prior knowledge. One is the quote unquote empirical base, and the other one is the hierarchical model.
Yeah, the hierarchical model indicates of the value is much away from 2,500 and close to 4,400 is an indication that the four data sets are not entirely similar. And the random effects model controls the borrowing of information, so it shrinks a bit, but not overwhelmingly shrinking it. So that's what the numbers indicates. Yep, go ahead.
Good. So now we're going to get to one of our favorite examples, that's the determining shelf life limits. And this is what we're going to show you how to use a power prior. This is a shameless.
Jose, this is well, it's almost the top of the hour. Shall we just take a couple of questions? Stan, if
Sure. Let's stop here and do that. But what I was going to say before we go on, this is a shameless, self-promotion. Fan and I just gave a presentation on this example at the nonclinical biostat conference last month, and then we're going to give a variation of the same talk at the IABS conference in November. So yes, go ahead. Let's take some questions.
Okay, so we can do two fast ones. Can you hear me, Jose?
Yes.
Yes.
Okay, so this is one that is pretty a common concern. Slide 19, why using a MLE estimation? We could fit a Bayesian model on the historical data with non-informative priors and use the posterior of that model as prior for the next one.
Yes. Yes. This is a good question. So let me just sort of maybe we should go back to the slides 19. I just to be very fast about it. Just so audience can see slides 19, Jose, if you don't mind going back.
Okay, so let me try to do that. Go ahead, you can start talking about
there's two ways of doing it. We get the MLE and we say the MLE has this mean and variance, and we're just going to use that as a way to approximate finding a prior. The alternative, what's being suggested, is that we can just do a posterior sample draw from the 199 data points and say we get 20,000 data sets, and then this is a 20,000 bivariate distribution, and can we just use that this data set as a way to construct somehow an empirical prior for the prior on phi and the p? Yes, this is completely doable. You can do that, and you can even non-parametrically using kernel density to do that. It is costly because you got to compute the two-dimensional kernel density, or you can use the 20,000 observation to jointly Bayesianly estimate the values of the gamma hyperparameter and the beta hyperparameter. Yes, this is all doable. We think in this case, because 199 observation gives fairly concentrated prior, both approach would yield to very similar results.
And we actually did that. It's interesting that you're asking that question, because when Stan was reviewing these materials, he asked that question, and maybe we'll have it for the next webinar. We have some of the response there where we did the Bayesian, and you can see that the estimates come very close. So as Fan was saying, this is a way faster way of doing this. But because you're going to end up at the same place. And the reason being here, as Fan mentioned, is because we have a big sample size of 199 observations. But yes, the answer to your question is yes.
Right, and if you are if you are truly in doubt, one is to actually using the gamma approximation to see overlay what the posterior sample would look like. And if they look similar enough, then you say good enough.
Okay.
Yeah.
Thank you.
Okay, one more question, and then we can move on. This is related to the prior distributions on both the empirical and hierarchical models. How do we know that these distributions are appropriate?
Oh, yeah. Okay, so the prior distribution
We're gonna
random effects. That's on page 29.
Yes, so let's go there. Yes.
So the prior distribution on the random effects, they themselves is a very, very contentious issue in Bayesian statistics, because they essentially still controls the amount of shrinkage, and different amount of shrinkage implies different results. And so one question is whether there should be a correct prior. I personally think there's no such a thing called prior, because prior represents how much you think similar and dissimilar these random effects should be to each other. And by the way, this is a question empirical Bayes is trying to answer, is that they will say, well, I don't know what they need to be, so I'm not going to let my data to inform it directly. It has its own problem. But it's along the same line of the philosophical and practical debate on how to construct these prior. I personally don't think there is a correct prior. I do think there is a general consensus of having relatively diffused hyperlevel prior distribution on the random effects. But yes.
But having said that, we know some things about the parameters, and this is what we say, the parameter 5 is greater than 0, so it makes sense to use a positive distribution. A log normal is something that is easy to work with, but you can use a Weibull distribution. Gamma may not work well, because gamma, based on our experiences and experience of other people, that's a good distribution for dispersion parameters. But that's why we're selecting the log normal. And the P, that's a no-brainer, because that is a parameter that is between 0 and 1. And for most applications, the beta distribution is the one that works. So based on those two things, we think that these are reasonable choices for this.
And I want to add one more comment to this whole discussion, and you can see that the same question would come up with many discussions in the literature. So I don't want to oversaying one way or the other. But in essence, if there is enough information in the data to inform what the random effects need to be, which is the case, seem to be, because there is enough cluster sample size in each one of them. In those situations, the specific hyperprior distributions seem to matter less significantly. But if the cluster size is small and you still want to have some sort of shrinkage, then these prior comes in a much more significant way. And there are ways of dealing with it. And we can teach a seminar on that completely by itself.
Yeah, many of these.
It is a contentious issue. It's a really contentious issue.
Yeah.
Yes. So people think that it's just between the frequentists and the Bayesian. Within the Bayesian world, there's a lot of contentions and discussions on how to do this, because it's not up. But we're just sharing some ideas as to what may be appropriate, at least for this particular example. And the beauty about this is you can do a sensitivity analysis. You can say, okay, I'm not going to use a log normal. Let me try a Weibull and see what I get, and see what happens. So that's possible too. So now we're going to get into this example, one of our favorite examples. So we need some expiry limits for this monoclonal antibody molecule that we have, and we have limited data. We only have 7 lots, and this data is data over time. This is called stability data. For those of you who are not familiar with it, for those of you who are familiar with it, it's in the data, and that's the actual way the data looks. Is some look a little funky, some go up. In general, they're going up. So we have that data. What can we do with that? This is very similar to the other example where we only have 4 data points. Even though we have several data points per lot, we only have 7 lots. In essence, we're trying to capture the lot-to-lot variation. So an estimate of variance with only 6 degrees of freedom is not that strong. But we do have information on like monoclonal antibodies, molecules. And some of this varied by the subject matter expert. And this is where we get into this discussion into the discipline objectivity. We mentioned this in previous webinars. Is something that is an agreement between a group of scientists and engineers of what these molecules may be like, quote unquote. And these are these. So in this case, we have 4 of them, and you can see the data there for the 4 of them. And we're going to tell you what the response we're looking at. So the idea here is we have these 7 lots, and this is happening more and more because there's a push for accelerated introduction of drugs, like we did with the COVID vaccines. And sometimes you don't have enough time to collect the data. So if you have only 7, what can we do? Okay. So this is the case study design. So we're going to select this stability data set, and this is actually, those 7 lots came from an original data set that had 14 lots that was used for a marketing application, submission and all that. So we know, we have the history, we know what the numbers are that we used. So here, a person we work with, Executive Director of Product Quality, Executive Director at Amgen, she went to a conference and she heard this thing about Bayesian statistics that was a way to use prior knowledge. And prior knowledge, we keep repeating that, but that's a hot phrase within CMC. And she wanted to know if we can do this, So she said, we're going to do a test and see if we select some lots. And she did the selection. We select 7 lots out of the 14. And we combine that with information from like molecules from 4 of them. Can we recover the information from the original data set? Can we recover, if we use these 7 plus these 4, can we recover that? So that is the comparison of this analysis with that. Actually, what I think this was a test for us statisticians. I think she not only wanted to test the Bayesian stat, but she wanted to see, if we could do it. So this is the description. The original data set, it was an IgG1. Ig stands for immunoglobulin, which some of the things in your body that react to viruses and infections and all that, and there are different types. Some of them have different reactions than others. So this is an IgG1. We had 14 lots that were stored as minus 30C, and what we needed there was the expiry and the limits at 48 months. Okay, that's kind of like the expiration date or goodbye used to by that day. So there were 7 lots selected, 3 lots had data to 6 months, 3 lots to 6, 12, and 24 months, and 1 lot up to 24 months. So notice it's not only that we only have 7 lots, we have limited time data. We want to predict to 48, which is twice that. And normally, for those of you familiar with the ICH Q1E guidance, normally we don't go past 12 months. But with the original data set, since we had that data, that was the expiry that was generated, so we needed to compare to that. And what we're looking at here is the high molecular weight. SE stands for size exclusion. HPLC is the method that is used to measure that. And these are impurities. These are things that we want to control in our product. So high molecular weight is a key one, is HMW. And now the data sets, we have 4 monoclonal antibodies, same family. 2 of them are IgG1s and 2 of them are IgG2s. 1 lot has 11, the other one has 8, 10, and 11. So we're going to use all that. And they were also stored at the same temperature. So you can see that the maps share some characteristics. So how do we do this? We're going to use a beta mixed model. And why are we using a beta mixed model? Well, the high molecular weight is also a quantity between 0 and 1. It's an impurity, 0% to 100%. So as we have used it in the past for viability, remember when we computed tolerance bound, the lower tolerance bound for viability data, that was a quantity between 0 and 1. And that's an appropriate distribution for that. We used that just now. We had a discussion using the beta distribution as a prior for the P parameter in the negative binomial. We also want to capture the lot variation around time 0, which means the intercepts. We want to allow for different intercepts. And the degradation rate, that's the slope. We also want to capture the lot-to-lot variation around there. But we also want to capture the variation as a function of time. One of the things that happens, some of you may be familiar with that, is that the variation increases with time. And a lot of times when we do this analysis, that's not taken into account. We have prior knowledge, we have 4 molecules. When we did the hierarchical model, we had 1 plus 3. Here we're going to have 1 plus 4. And we're going to use the power prior. And power prior is great because it allows to weight the prior knowledge that we have. We're going to show you that. Okay. So here, again, high molecular weight, HMW is a quantity between 0 and 1. We're going to use the beta distribution. And we're going to use the parametrization of Ferrari and Crivare-Neto. Silvia Ferrari is a professor in Sao Paulo, University of Sao Paulo in Brazil, and Francisco Crivare-Neto is a professor, I think, at the University of Pernambuco. They're both from Brazil. And this is a very popular parametrization for beta regression. If you use PROC BGLIMM makes and you feed a beta distribution behind the scenes, what BGLIMM uses is the Ferrari Crivare-Neto parametrization. What this allows us to do is we're going to have regression models both for the location and dispersion. We just mentioned that variation changes over time. We want to model that. So for location, we have your traditional logistic regression. What that means is the logic of mu, this is a generalized linear model, is a function of time, months. There's an intercept and slope, but that's the random coefficients. Remember, we want to allow variation at time 0, which is the intercept, and we're going to allow variation around the degradation rate, which is the slope. And that variation comes from the lots, the 7 lots that we have. So we're going to have 7 intercepts and the slope to slope variation. And then for dispersion, we're going to use a log dispersion, meaning the log of the dispersion parameter. Remember, phi in the negative binomial is related to the over-dispersion, or let me put it the other way. The over-dispersion parameter Q is a function of phi. So what we're going to do is we're going to fit a linear model to that. So we're using a Bayesian beta regression random coefficients model to give it a big name. In terms of the choice of priors, and this could be a discussion how to do this. For regression coefficients in general, I don't know if it's a consensus, but at least some people like some expert like Professor Gelman, they suggest using a half Cauchy and a half T for the parameters of a regression. So that's what we're doing here with the intercept and the slope. For the dispersion coefficients, we're going to use a normal with a large variance. And for the random coefficients, here is the lot-to-lot variation. Before in the hierarchical model was a data set to data set variation. Here, we're going to use a normal for the means and an inverse gamma for the variances. Again, this is where there are discussions. For example, Professor Gelman wrote a paper on prior parameter surveillance components, and he does not suggest that people use the inverse gamma distribution. He suggests that we use the half Cauchy or something else. We tried that, and it didn't work well. And we haven't have time to investigate this, but one of the things that I mentioned to Fang is that I imagine that when they did this research, the models that were fitting with were probably with a normal distribution, but here the likelihood that we're using is a beta distribution, and that may have something to do with that. But we have found that of all the sensitivity analysis that we did, the inverse gamma works well.
I should have a note on saying about having inverse gamma with small shape and scale. This prior is, if you plot the prior, is very peaky to, I think I mentioned it's peaky to 0 and has a thicker tail to the right. The prior is made popular because of Weinberg's in the 90s when in the example. Yes. For that similar. And the reason it did that is that the prior is it looks similar to the Jeffreys prior on the variance, which is 1 over the variance square. But unfortunately, it's improper prior, which leads to improper posterior. So the inverse gamma, or the gamma on the precision, and inverse gamma on the variance, is a good approximation shape-wise to that. To the Jeffreys prior, and this is has its own merit. In the 2006 Gelman paper on prior discussion, he thought that this prior was too informative in the examples that he showed, and he recommended against it. But as all things, it's part of the contentious issue. It's not, informative and non-informative. It's a relative issue. But in this particular case, we think it works reasonably well.
Yeah.
But you don't have to. I mean, you don't have to.
Exactly. Yeah. And that's the part that we mentioned about the sensitivity analysis. We try this with the half code sheet that they recommend in these situations, and this is the one that we found that works the best. And I was going to ask you, Fang, this inverse gamma with the normal, isn't that the conjugate prior if you have a normal situation when you don't know them?
Inverse gamma on the variance or the gamma on the precision, yes, it is a conjugate prior, so helpful sampling.
So these are the priors that we're going to use. And now you can see that this is a little more elaborate as we were seeing with the hierarchical model, because you had to keep track of a whole bunch of things. That's the only thing that you had to pay attention to, be like a good accountant, so you know where things are coming. You have multiple parameters, multiple priors that you have to specify. So what prior are we going to use? Okay? We're going to use the proper prior. So again, as we mentioned before, what we're trying to do here is to connect the data that we have. Notice we have 4 map data sets that we want to connect to some prior. So we can use that in a Bayesian analysis.
Just so that we are clear on this, this is 2 sets of prior we're talking about. There is a within data, so just people don't get confused. So there is a within each study that's a random effects prior. So that's what we just discussed. And now because we have multiple data sets, we're going to have a power prior on top of that. So that's why we just discussed the random effects model without showing you any code. We are moving on to talking about the power prior right away. So there are two different things, but that is jointly put together for that reason.
Yeah, and we're going to show you the code. So again, we want to find the priors and then connect the data to that. So we're going to use a power prior. There's a paper from 2000 by Ibrahim and Chen.
Not me.
Not this Fang Chen, but he appears.
Minghui from UConn.
He appears in another paper with Ibrahim. We'll talk about that. So they provide a class of informative priors that is very, very helpful. And then this, in the sense that if you have historical data, that's one way to go. And that's what we have here, and it's called the power prior. So what is the power prior? Okay. So we have,
Go ahead. I'm sorry. I didn't mean to interrupt you. I was just going to say that the whole idea. Just want to stress the power prior is to translate information from the data to a prior distribution through the idea of similarly of a Bayesian analysis of it.
Yeah. So here we have these historical data sets, and what we're going to assume is the beta distribution applies to all of them because it's high molecular weight data for all of them. And this is a power prior. The power prior is proportional to a power of the likelihood times the prior. Okay. So this A naught here, this power parameter, is between 0 and 1, and that power parameter is the one that controls the amount of weight that you give to your historical data. Here, your data set is D0, it shows one of them. We'll show you how that's done in the code. But this is what controls that. So if...
So let me just add on one thing onto it. Just to imagine if you have a historical data and you were to do a Bayesian analysis, you would just do likelihood times whatever the prior that you would use on theta. Okay, so that would just be your posterior distribution. Okay, which in the case, if you use that as your current analysis, would just be the same as combining your historical data with the current data and do a informal analysis on them all. What Joe Abraham and Minghui Chen thought is that might be too informative. So we going to suggest raising the likelihood on the original historical data to a power discounting parameter of A naught. So that's why this A naught need to be between 0 and 1. It can't be like 50 or it can't be negative 20. It needs to be between 0 and 1 as an indication that if it's small, then I'm discounting the weight coming from the historical data likelihood. If it's closer to 1, I'm using more of that information.
Which is what we have here. as you just said, if it's 1, we're completely pulling the information because this disappears. So if you're traditional Bayes, if this is 0, then you're getting rid of the historical data. But if you put something in between, like 0.5, then you're borrowing from the historical data set by a certain weight, you know.
Yeah.
And Fang always cringes when I say, oh, this is 50%. It's not 50%, you know, but I think of that as, you know, I'm borrowing 50% of the historical data, but it's not
Right.
quite like that.
Right, it's not quite like that.
But that's the way that. But the thing here is that each data set is going to get its own weight. Okay, so you're going to have an A naught for data set 1, 1 for data set 2, 1 for data set 3, and 1 for data set 4. The beauty of this is, you know, for this example, we're going to use the same weight, but you can apply different weights. So remember, we had 2 IgG1s and 2 IgG2s, and the data set is an IgG1. So we make the case that the IgG1 should have more weight because they're more alike to the data at hand than the IgG2. So that can be controlled by the weights. And we're going to show you how the weights come into play. Okay, so let's look at the MCMC code because this will hopefully help you understand a little bit. So there's several pages of this.
Yeah, there are 2 parts to understand. And one is setting up the random effects for each individual study, and one is a weighting for each of the likelihood as in terms of the power prior. So setting up the likelihood is the code is just having different parameters, and then there is different intercepts model and the betas and alphas, and then each have their own different prior distributions.
Yeah. And this is what we're saying, that you have to be good at keeping track of everything.
Right.
Just a point here, you know, we wrote out all the parameters here in the monitor statement. You remember the monitor statement is the one that allows you to monitor them and generate the samples in the data set. If you don't put it in the monitor, it won't be the data set. Now there is a shorthand for that. So those of you who are very good at this will be looking at this as how these guys are novices. So you can use the shorthand notation underscore params underscore to do what?
Yeah, and then it will automatically monitors all parameters that define in the PROC statement. You would only use it if you want to monitor additional symbols, like the phi's to the end of the right, the first line to the right, because by default all the parameters come out in terms of posterior inferences and estimation. So but if you want to do something extra, so that's what you need as a shorthand notion of it. And the prior distribution, and I think they are fairly standard.
Yeah, so these are the normal, the inverse gamma, the half T, which is very similar to the half Cauchy. Now these are the models. So this is the piece of code that is dealing with the random effects here.
Right, the random effects are just random effects, and say has a normal prior with a hyperparameter, which we had prior in the first page, and then there is a subject which tells you lot-to-lot variations of it. So you can imagine that in this particular data set, every study, every lot is lumped together, and each lot has a lot indicator, which I think is the same as a molecule, because the molecule is for each, you know, has a law and also has a molecule. Molecule goes from MAB1 or MAB1 to 3, 4, and a 0. And so you can just see that for location of random coefficients in the same slope model is the next line. For different molecule, we are constructing different mu and phi parameters in the slope model. So this is a lot of if statement.
So this is the within molecule variation, the lot-to-lot. Remember, we talk about lot-to-lot variation in the intercepts and the slope. Okay, so this is the location random coefficients model. So you have an intercept and you have the random effect of that intercept. This int mu is this random effect. This is the lot-to-lot variation at time 0. This LSP mu is the lot-to-lot variation for the slope or degradation rate, and this is just that. We are assuming that they're all going to have the same degradation rate because they describe the same phenomenon for high molecular weight. That's again another assumption that you may need to check or you can modify. And then this model is the linear model for the dispersion, the phi. The phi is the dispersion. So you have an intercept and you have a slope times time. Yeah.
Right. And then it's just a transformation of the logic link and the mu and the phi computation. For that, that's the I don't know. It's just a logic.
Yeah. So this is remember we did logistic regression for the location, the log dispersion for the dispersion parameters. That's just going back. This is the inverse of the logic. And then here
just the power prior weights for different for different 4 different molecules data sets.
The historical ones, no? The prior
historical data sets, the historical data sets. So each is we're going to weight 0.5 as how much weight is used in the hyperprior. Okay, so in the power prior, that's what I meant. So the next code, the next line is defining the log likelihood to be the beta distribution for the results in alpha and beta. This is in essence for the current data set. But if for any other molecules, that likelihood is being weighted by different historical weights of the discounting parameter of A0 and 0.05 and such. Because they're the same, we could simplify the code by just weighting it all by 0.5. But we want to illustrate using the code here to say that you can use changing the A0 0 to be different, and this code is sort of more general for that purpose.
Exactly. So this could be a 0.1, this could be a 0.9.
Yeah.
And then again, this is the power. Since we're in the log likelihood, then the power becomes multiplication. So
oh yes, I should mention
this times the log likelihood.
It's the power discounting times the log likelihood as
log likelihood. That's the other.
Yeah.
And then result B is the response. That's the high molecular weight, and we're using a general likelihood because that's the one we use when we define the likelihood. So that's the code. It's a little more elaborate, but by now, based on what we had shown you in the past 2 webinars, you have a sense for what this is. As we said, we just have to be a little more meticulous in keeping track of things. Okay, so let's talk about the results. So this is the data. Those are the 7 lots. So we had data for some lots out to 24. We want to predict out to 48. But the main point here is to come up with tolerance bands at 48. Okay, so we have data on 4 like quote unquote maps. And these are the results. So one thing to notice here, what you're looking at is the prediction line, that's this blue line here. And then you have at 24, the prediction is 1.4%. At 48, the prediction is 1.58%. And these are the posterior distributions at each time point. This is beautiful for me because at each time point, you have a posterior distribution. So if you want the tolerance bounds, what you need are the quantiles of these distributions. So at 48 months, these red lines are the quantiles of that distribution. We want a 99% coverage. So these are the limits that leave 99% of that. So you notice that this distribution is a little skew. Why? Because that's the beta distribution. So you can see that the variation, the fatness of the distribution increases with time. And that makes sense in different ways. One, here we have a lot of data. So there's less uncertainty here than here. We don't have data here. The latest data points, we have 2 data points at 24. So it is increasing with time. And remember, we use a log dispersion model for that. And my favorite thing, because it's my pet peeve, we have a positive distributions. There are no negative results. When this is done, people use the normal distribution. And what happens is if you're close to this limit 0, you're going to have negative numbers, which absolutely make no sense because high molecular weight cannot be negative. So what people tend to do is just truncate that to 0. So the prior knowledge is going to help with a small sample size of 7 lots, and it's going to decrease the band. We're showing you the band here. We don't show you the decrease yet, but the band here at 48 months is 0.6% to 3.25%. So that will be the basis to set up some expiry limits at 48, done the Bayesian way. Again, this is done with 7 lots and prior knowledge. And we're using the weight of 0.5. How do we select the weight of 0.5? There are different ways of doing that. One of them is doing a sensitivity analysis, which means try different A0. So these will be A0 equals 0. We're going to discard all the information. So you can see a lot of uncertainty here. Now, if you use A0 0.1 and using 0.1 for each of the 4 data sets, 0.2, 0.3, 0.4, 0.5, all the way 1. And remember, if you use a power of 1, that means you're combining all the 4 data sets with the current data set. So you have combination of the 5 data sets. That will be that. Okay. So now you can see here that 0.5 provides a reasonable choice. The line here is the limit obtained with 0.5, which is 3.25. You can see if you go to 0.6, 0.7, 0.8, 0.9, even at 0.1, there's not much change. So you can kind of stop there and use that. So if
there is always a big discussion on what is the correct usage of how to pick this A0, or whether A0 should be considered as a random parameter that can be estimated by the data. There are different ways of doing it. We didn't go through the exercise. You could, one can use, say, a model fitting selection criteria like the DIC to kind of tell what would be a good A0 value to use. But in this particular case, when we did the sensitivity analysis, we visualized over a range of the values. 0.5 seemed to give a good reasonable weights between not borrowing too much and not affecting between the two. So we just,
if you look at this in detail, yes. So if we use only 0.1, just a little bit of the historical data, you can already see that there is a substantial reduction from not using any of the historical data to using a little bit of the historical data. There's a substantial reduction in the upper bound. If you use full borrowing 0.1, equivalent to putting all the data, we believe that may raise more questions, especially from the regulatory agencies, because what you're doing is, okay, I have this data set, I'm just going to add, because I only have 7 lots, I'm going to add more data to it to get a better limit. So that's not quite right. So we try to shy away from the 0.1. Half borrowing, which is what we just mentioned, it just so has as much effects as the full borrowing, and it's halfway between that.
Yeah.
And as you just said, we can use other criteria to choose the weight.
And I also want to add why in the first bullet, when you see that we only borrowed a little bit, the difference between borrowing nothing and borrowing even a little bit shows a substantial reduction in tolerance interval. It really is the indication of how similar these data sets are. So the idea of borrowing is always when there is a data set similar, you want to borrow, you are capable of borrowing more, and borrowing a little bit will lead to a great amount of effects. And if they are very dissimilar, you potentially want to borrow less. So by looking at the effects of not borrowing to borrowing one, a drastic reduction is an indication of that. But that's really a discussion of different costs. So.
Exactly. And again, this will be some discussions that people will have with the agency, showing the sensitivity analysis and all that. As we mentioned at the beginning, in all these things, we have to be very transparent as to the choice of priors parameters and the stuff. That's why we're showing you the sensitivity analysis. So this is the answer to the challenge. So on the left, you have the frequentist approach. This is coming from a paper by Hoffman and Kringle that they show how to generate tolerance intervals when you have one random effect. So this is done at each slice by slice, at each time point. You do that, it's not quite a regression. And as we mentioned before, this is not a true variance component analysis. It's more an adjustment on the n effective size and adjusting the variance component for that. We use that when we looked at the Wolfinger's paper and the variance component. So drum roll, please. If you get here, the limits were 0.3 to 2.9, and this is the Bayesian analysis. The limits are 0.6 to 3.25. So based on this, you can see that the Bayesian analysis was able to recover the information. These are the 14 lots here. The other thing, some of you may be looking at these bands. When I looked at those bands, they made me feel a little uncomfortable because they pretty much do not change with time. Here you can see that, as we mentioned before, where we have a lot of data, the bands are narrower. These bands are narrower than these bands. And then, of course, we don't have any data at 48 or 36. They get wider and wider. So in terms of the challenge, we were able to recover the information. Now, let's just show you what the prior knowledge does. As we saw when you use a NOT, if you don't use any information, let's say you grab those 7 lots and you're a Bayesian and say, okay, I'm going to use some non-informative priors and I'm going to do some Bayesian analysis. If you do that, then you can see what happens, and you get a limit of 0.2 to 12, 11.85%. So this distribution here is pretty long because we not only have no data here, but we only have 7 lots. So what happens if we use a weight of 0.5? Then you get that. On this side, we have the 7 lots plus the 11, 8, 10, and 11 from the other molecules. And that's the limit that we show you of 0.5 to 3.25. So in fact, half borrowing cuts the upper tolerance bound by 364%. We mentioned in a few slides back that this use of prior knowledge via this analysis and the prior does help the interval. So again, this is why we were able to recover the information from the full data set. And just to show you one more thing, even if you use 0.1, even just a little bit of borrowing, cuts the limit by 230%. The limit, again, with no prior information is 12%, 11.85. The limit, if you just borrow 0.1, goes down to 5%. Okay, so that's the beauty of this approach. So the borrowing really can improve the tolerance interval when you have a small sample size. So this was, as I said, a test case and demonstrated that this has potential. We actually did it with another parameter, the CX acidic, and we got very similar results. We were able to recover the information from the 14 lots. So just a few things here, how this power prior works, and it has some attractive theoretical properties. So hopefully you're able to see,
right. There's a fairly large discussion in historical borrowing, which I think at this point we're running short on time, so maybe we should just move forward. It really is a wide reach of literature discussion here.
There's one more thing that we want to show you, and I'm pretty sure that a lot of you get involved in this, is the issue of internal release limits. You have this data, and we just defined some limits for that at 48 months, and those were 0.6 to 3.25. But what we want internally as a producer, as a manufacturer of this, is we want to set some limits at time 0. So if I see a lot that is behaving oddly, then we're not going to make it out to 48. So these internal release limits is a way of having this information, having these models and this limit at 48. Can I go back and set some limits at time 0? That's called internal release limit. They don't have to be at time 0. You can do this exercise maybe at 10 months, 6 months, whatever it may be appropriate for you, but it's usually done at time 0. Okay. So this is just a definition. And yes, that's Alton, that's Stan, that's our moderator. We're very honored to have him be a moderator for us. And he has a very nice paper, recent, 2018, on internal release limits. So if you're not familiar with this, even if you are familiar with this, they do a great job at summarizing all the frequentist type techniques. So again, 1 or 2-sided bounds that are going to ensure that the batch is going to make it to the end. Okay. There's another definition, just a window. Okay, again, time 0. That if we're here, if we are within this limit at time 0, then there's a high chance, there's a big chance, a big probability, large probability that we're going to make it to 48 months in this case. Again, from their paper, okay, they're just telling you how this is done in the frequentist point of view. Okay, and this is one of my favorite quotes, I was mentioning that to Stan earlier. The batch differences, that's the batch to batch. Batch here is what we call lot. That's the lot to lot variation. And it's just, it complicates the calculations. You saw how elaborate the calculations were because we're taking into account the lot to lot variation. We need to take into account for each of the data sets the within lot variation at time 0, okay? And that's the intercept, the different intercepts for the different lots, and the different variation around the slope for the different lots. So that's a random effect. So if you're in the frequentist framework, that will be a mixed effect model. Okay. But from the Bayesian perspective, we just want to find that interval that when the time 0 is there, then at the end you're gonna have a high probability of being within the spec. LSL is the lower specification limit. USL is the upper specification limit. You can think of those as the limit that were derived using the tolerance interval. And we put confidence here because that's the way we will think of it if we're frequentist, but it's a probability from the Bayesian point of view of probability. So we want to have a high probability, 95%, that the batch is going to be within those lower and upper specification at time 48 if they're within the internal release limit at time 0. These calculations are a little more elaborate. They're based on what we call the probability of success, the POS, which is a probability that the complete data time 0 all the way to SL. SL stands for shelf life. In our case, it's 48, that you're going to be at the end there. If you have a linear regression like we have, then it's kind of finding that, but you can reduce it. Finding this is the joint probability at time 0 and shelf life. So what we do here in these calculations is to find the joint probability at time 0 and time 48 to be within the lower specification and upper specification limit. Again, LSS is lower specification limit, USL upper specification limit, and we want that to be greater than 0.95. Okay, so if you look at what we did, this is a 3 1/4, and this is a 0.6. What we want is limits here at time 0. That if a batch is within these limits, there's a 95% probability that it's going to be within 0.6 and 3 1/4. You know, so that's what we want. So how do we find these two things? So this is kind of like the recipe to do that. You have to fit them all to the data. We've done that. This is the Bayesian beta regression random coefficients that we just saw. And now we're going to compute the predicted distribution. And we mentioned the predicted distribution last time when we were looking at the variance component, and we were talking about the different types of, or the two main types of tolerance intervals, the content and the expectation. And we say, if you want a beta content tolerance interval, then you have to use a graphical procedure proposed by Wolfinger and modified slightly by Krishnamurti. And then we said, if you want a beta expectation type interval, then you use a credible interval around the predicted distribution. So the predicted distribution is just the data in the future. So we calculate the probability of success with that, and then we estimate those limits. Okay. So this is what we did. And remember, we got 0.55 to 3 1/4. We went through this exercise. We used the power prior with 0.5, and that gave us a tolerant limit. And then here, it's a little, we're not gonna get into all the details, but it's just what the predicted distribution is the probability of the data, of the future data, given the data at hand, and that includes, this is the posterior here.
Yeah, this is a very Bayesian concept in the sense of you want to, the pi of y predict given y is you want to predict your future y given your current y without parameters, because in Bayesian don't conditioned on parameter value. So what does that mean? That means the random variable theta need to be integrated out. Once it's integrated out, we got to integrate with respect to what? To respect the posterior. So in the sense of this integral makes sense, giving the current data informs the parameter, and we integrate the parameter and we make the prediction. So that's what the predictive distribution is about.
Yeah. And it's a very nice concept because then you're predicting data. based on the data that you have, plus all the Bayesian machinery that you put in there. So it's a great way of simulating what your actual data is going to be, if all the conditions are the same. So we do that. There are ways of doing that. So we just essentially drawing random samples from the random effects. In this case, it's a little more complicated. The code is there. Again, in the interest of time, you're going to get this in the notes. But this is the model that we're doing. And the only difference here, let me go back, is that here, these are the probability of success that we define in the POSs. And remember, the 3 1/4 was the upper limit, and the 0.55 is the lower limit. And 0t is times 0, so you do it at times 0. And SL is shelf life. Shelf life for us is 48. So you're computing the probability that it's going to be within the specifications at time 0, then at time 48, and then you're computing the joint probabilities for that. And then you get a plot like that. That is your probability of success curve. And here you have your data. This is the actual error, goes from 0 to 4%, and it goes up. And then you'll have the line at 0.95. So what we're going to do is find the intersection that's going to define the limits that we need. So if we do that, those are the limits. So if we want this joint probability at time 0 and time 48, that we're going to meet the specification of 0.55 and 3 1/4, then we need these limits. Again, if we want this to be at least 95%, then we want the limits to be 0.76 and 281. 0.76 and 281. And those are the limits at time 0. Again, if you have a batch and you measure the high molecular weight at time 0, and that high molecular weight is between 0.76 and 2.81, there is a 95% probability that after 48 months, the high molecular weight of that batch is going to be between 0.55 and 3 1/4, which is what we want. Now, if you have a batch that has a high molecular weight less than 0.76 or greater than 2.81, then it may require something else. But based on the analysis, you will investigate that law. Okay? So again, the red lines here are the limits, and that's how this is done. And at the end here, this is from Stan's paper, and if you follow their approach, this graph is from their paper, then you get limits that are 135, 245. Remember, limit was 0.8 to 2.8, a little wider. And this is something that you'll realize whenever you use these Bayesian techniques, because we're bringing information from different data sets. That variation is getting into our estimates and is improving things. You use a more, I'm going to say, realistic picture of what things can be. So this could be a little conservative, but that's the main difference. So we're almost at the end. We're going to entertain some questions, but one thing that we want to talk about is these truly informative priors. I've said this many times before. This is connecting the data to the priors and all that. I mentioned that I did a lot of work in reliability, and in reliability, it's a discipline that you can really elicit this prior information. For example, the Weibull distribution that goes back to 1951. It's been used now for 60 years. We should update that. So there's a lot of information in this Weibull distribution. It's widely used in reliability work. So we can use that information to gather that. I don't see that much different from CMC because we do have historical information. So for example, in certain industries, you have these tables where they tell you what the expected beta parameter is for different applications. One of those companies is GE, and most of us are familiar with GE with appliances, because that's what we get to see. But actually, GE is bigger than that. They used to be in the financial business. I don't think they're there anymore, but they make jet engines and locomotive engines, and for those, they have a very, very good reliability program. It's impressive what they do. And if you go to their website, you'll see a table like that. So this is the Weibull analysis information for a whole bunch of different things. So for example, if you're dealing with a locomotive oil and you want to check the filter oil, but the beta parameter for your Weibull distribution has a typical value of 1.1 and is anywhere between 0.5 and 1.4. Your characteristic life, which is the eta parameter in the Weibull, is about 1042, can be as low as 883, and it can be as high as 5208. So you can see that these tables are perfect for generating prior information because it tells you what the expected value is, gives you a range to define the variance. And if you're using a Weibull, for example, then we'll use the this info macro. We'll put this mean and variance, and then we'll get parameters for the different. But the thing is that these are generated from many industries, many studies, and from subject matter expertise. So we see these as truly informative prior. So our vision for CMC, is a wish. Maybe the consortium, we can all work together, member companies, and create these quote unquote tables with the statistical information about common maps performance indicators like the size exclusion and CEX, and say, okay, if you're doing this type of analysis and you're using this Bayesian analysis for this beta distribution or this gamma distribution, you expect these parameters to be in this range. Could be also be very nice, we didn't put it in here, is to have a catalog of useful priors that people can go and choose from. We did that. There's a catalog by Yang and Berger, and we have used a lot of the priors from there. It's very, very handy, and they have it by distribution. So if you're working with the beta distribution, you use the tri-gamma as a prior, and we used that before when we deal with viability data. So Bayesian statistics, we can incorporate prior knowledge. Hopefully you've seen that. And you can see that we can use it in many, many contexts here. And some industry discussions are starting to happen. We had one, a very fruitful one. Stan was involved in that at the CMC conference, BC conference, non-clinical biostat conference in June. And the time has come, I believe. So we were hoping that we had people from regulatory agencies here. Hopefully some of them were able to attend so they can see how some of these things can be used in industry. Some of the references here for you, the paper by Robbins for the empirical base. This is a paper, and this is the right F. Chang. So this is a very nice paper on the power prior. It goes through all the details and all that. And that's the paper by Stan Alton on the release limits. And then we just want to finish with Professor Box. Hopefully a lot of you, if not most of you, have heard that phrase. And we're lucky that, most of the time they give credit to him because it's his phrase. If you're really lucky, you may see a more complete phrase that says all models are wrong, but some are useful. Actually, Professor Box had several variations of this phrase, and this is just a snippet, a soundbite. But this is one from a 1979 paper called Some Problems of Statistics and Everyday Life. It's an easy read, one of my favorite papers, and this is what he had to say. So we hope that you have found this webinar useful, and not only that, that you have seen the scope and the power of all these Bayesian techniques, and hopefully they'll be useful in your work. At this time, we'll take some questions, and we'll stay over 5 minutes or more if you're okay with that, so we can answer all the questions you may have. Thank you so much.
Yep, thank you all very much. Appreciate it.
Okay, we have 3 or 4 questions in queue. The first one is there a pool of different priors relevant to a particular statistical topic, say like stability, for instance, that we could choose the best prior going forward? So the question is how to do this. Can you comment on that?
Yes, and this is, I will say that's a vision of ours, that maybe via the IQ or other groups we can work on that. There's some recommendations if you're feeding regression models, there are some priors that you use for the regression coefficients and things like that. But I don't think there's a general consensus. Again, we have mentioned the paper by Gelman that he wrote on priors for variance components. the catalog by Yang and Berger is by distribution. So if you're working with data that is beta, that the beta distribution is a good approximation, then they show you what the Jeffers prior is, what a reference prior is, and all that. But to my knowledge, if you're working with stability data, there's nothing like that. And my hope is that we can come up with that as an industry, so we can all use that and generate several suggestions for that. For example, if you're working with quantities between 0 and 1, like high molecular weight, like viability, then we strongly recommend you use a beta distribution and not a normal, for example. But that's more on the likelihood side. But if you use that, then the priors will follow from that if you go to the Yang and Berger catalog.
In using MLE estimates from historical data sets as informative priors, not the power prior, is that considered as full borrowing?
Yeah, well, it depends on if the prior distribution, how well the prior distribution capture the MLE. Yeah, I would say it's pretty close to full borrowing. Yes.
Yeah, and we saw that. Yeah, we saw that shrinkage in the estimators. If you remember, when we did empirical base with the 199, we got a limit which was about 2,600 or so. If you use just the 199 observations and compute an upper bound using frequentist techniques, you get about 2,500. So it's very close. So that's what we meant, that, you know, that his prior was shrinking the mean towards the data. So yes, yeah.
So there are two ways of looking at it. One is that if you feel this is too much borrowing, you should just use a mixture prior, as we mentioned earlier. And the second is the reason of using a parametric distribution to approximate a results from historical analysis is that hopefully the parametric distribution has some interpretability. In that our particular case, it might not have this clear, but that is some advantage that you can have in using distribution to capture the information and have interpretation in your model. That's relevant.
Exactly, and just remember, we show you 3 ways of using prior knowledge. You know, so if you have multiple data sets, you know, we may tend to use something like the power prior, because you can be very specific as to specifying the weights and all that. But you know, you have the hierarchical model too that is very helpful. So I will see the empirical base is just those situations where you only have one data set and that's it that you can use. But in a lot of the CMC situations, I envision that a lot of you will have multiple data sets. Like in the case of the subvisible particles, we had 3 additional data sets. In the case of the stability data, we had 4 additional maps that we can tap. And it's probably more than 4 that you can tap into.
Thanks for your highly enthusiastic presentations is the comment. The use of these approaches will definitely increase as more practical tools with examples are shared in the form of books and presentations. That was one comment that came in.
Yeah.
Well, thanks for the comment. And in terms of books, again, a little bit self-publicity. I don't know if they're in the audience, but Paul Paya from Eli Lilly and Tony Pormahud, don't remember his company, they got the approval for CS Chapman Hall, CRC Press, and there's going to be a book next year on Bayesian applications in CMC. And there are different people, Stan included, writing different chapters. Fang and I are going to put this stability data example that you saw is going to be granted. If we get all the approvals, it's going to be a chapter in that book. So it would be wonderful to have that, you know, because that's something that it will give us more ammunition with regulatory agencies. So yes, that's coming. I think the time is right for all this, and that's one of the reasons that we did this. So you get excited like we are, and we start having conversations and sharing things and all that. And again, I'm serious. I will hope to see the IQ, the LSD, for example, sponsor something between companies that we can work, or maybe the ASA. I know they have a Bayesian section maybe the subsection for biotech can work on some of these things that we discussed.
Here's another question. Do we expect strong pushback from the agency on full borrowing?
You want to go first?
Probably.
Yeah,
I don't know.
yeah, probably. Yeah, and the reason is as we mentioned, you have this data set with 7 lots, and you have to do stability. 7 is a little on the low side. Full borrowing means not even doing the Bayesian, it's just adding more data to it. So you know that because you have 7 lots, you're going to get wide bands and all that. So you're just going to add that. So we believe that could be the case. I mean, we're going to get some pushback just by using Bayesian methods. And if you do full borrowing, there may be a stronger push than that. As we said at the beginning, on the clinical side, they're more receptive, and they're actually allowing for some of this. And I know there have been some submissions on the CMC side, but it's not something that they are widely accepting. I think you can go with a Bayesian method, but you have to have discussions and all that. So what we're suggesting is that you be very transparent into your choices of everything. As you can see, once you get into hierarchical models and the power prior, there are a lot of things that you have to keep track of. But I mean, we're hopeful. I think the time is right. So.
Do you have a?
I'm sorry. The last thing I was going to say. That's where I'm now. Is that I wanted to add the thing about the sensitivity analysis gives you a sense. So you can, for example, in what we show you, once you're at 0.5, there's not much gain by using all the data. So that's why we say that 0.5 was a reasonable choice. So we like doing sensitivity analysis. We think it's helpful as long as you have good graphs, good visualization of what things are happening, like the graph we show you with the tolerance bands.
Do you have a reference for the percent dist info macro?
I don't. I mean, I can send it to you. I mean, I think if you have a version of SAS that doesn't have it, I can send it to people.
Yeah.
Okay.
It should be part of the. It should be part of the core of the macros, no, in SAS fan.
Yeah, I think so. It depends. Maybe it may depend on the version of SAS.
Yeah. But send us an email. I mean, it's very helpful. I mean, you saw how it is. You just find those parameters either via MLE or non-parametrically and all that. You pass the name of the distribution that you're going to use, and then the mean and the variance. And that's why, if we have those tables, like the one I show you from GE, those tables give you the mean and the range. From the range, we can get a variance. And so now we have the 2 things that we have to pass to that macro with appropriate distribution. So,
unfortunately, the EMA reflection paper on statistics for comparability is not promising for accepting Bayes. Do you think this may change in the future? And again, this is related to a regulatory concern. So, do you have any comments on that?
Yes, I can comment. I was part of the team that went to London in 2017. It's amazing that it took 4 years for the paper to be finally published. But yes, I mean, I don't think they're opposed to it. If you read the reflection paper, one of the things that was encouraging to me is that they're not too opposed to different statistical techniques as long as you quantify the false positive rate. This is one of the things that they put there, that from the regulatory perspective, and I think I'm almost quoting verbatim, their main concern is the false positive rate of the statistical technique used. So I believe that if we use some Bayesian techniques and we address the false positive rate, they will be more receptive. The other point that they make, and this may connect to the multiplicity issue and all that, is that that's not enough, because we're doing, we may be doing equivalence with high molecular weight, with acidic, with maybe 4, 5, maybe 10 parameters. So they say that we have to take into account the overall false positive rate not just the one for a specific test. So that makes me hopeful that if we address that, then we can use some Bayesian techniques. Again, one of the things, this we have to work as an industry on that. And luckily for us, we have the SLG within the IQ. AAPS also has a CMC statistics group. But I encourage you to get involved and then work on this.
The last question we have, I think, is for Mahalia. Someone is asking, how should we go about getting copies of slides for the 4 sessions?
You just have to, Mahalia, go ahead.
Oh, okay. Yeah, you just need to send a message to me at my email, Mahalia Faegre. So it's Mahalia.
Mahalia, are you speaking? Your voice
We lost you.
Yeah, it faded out.
Are you able to hear me now?
Yes.
Yes.
Okay, all right, sorry about that. Just send an email to info, I-N-F-O, at iqconsortium.org and let me know which slide set that you would like, and I'll be happy to send them along.
Maybe you can type the email in the chat box to all audience so that people can see it.
Will do.
Thank you.
And so that's it. Thank you very much for a wonderful series of presentations, Fang and Jose. It was a great learning opportunity. I think I speak on behalf of all of the attendees, of which there were many from all the different companies. And thank you again, Mahalia, for organizing this and making the webinar possible.
Yeah,
So
thank you, Mahalia. Thank you really for all the technical aspects, for keeping us together, so to speak, and making sure everything is working. That's the behind the scenes stuff that makes this possible. So
right.
A virtual round of applause for Mahalia. And also a virtual round of applause for Stan for agreeing to, volunteering to do this.
Yeah.
Thank you all. Have a great summer. And we'll be in touch.
Okay. Goodbye, everyone.
Bye-bye.
Bye.